This video is going to cover line spectra and the Bohr model. One of the mysteries that scientists were trying to figure out in the early 20th century involved the emission spectra that was observed from energy emitted by atoms and molecules. These tubes are called spectra tubes, and they're really narrow tubes that are filled up with different gases. And when you put them into an electric source, they give off different wavelengths of light. And what scientists found is that every element gave off a different wavelength of light. If you take a white light source, like what you have here, and you shine it through a very narrow slit and then through a prism, it's going to produce the entire rainbow. We call that a continuous spectrum. If you take the spectra tubes from the previous slide with particular elements in them and shine those through a narrow opening and then through a prism, instead of getting the continuous spectrum, you just get discrete lines of it. The lines are separated and they're at particular wavelengths. Every element has a unique spectrum. The line spectra for hydrogen is fairly simple. It has lines at 4 wavelengths, and a man named John Balmer in 1885 found a relationship between these 4 wavelengths. The formula that is more commonly used now was developed by Johann Rydberg. It's this formula that you see here, where you've got the wavelength, which is what you would generally be solving for, times a constant, and then you've got N1 and N2. These are integers, and N2 is bigger than N1. This is an equation that we're really not going to use very often, but I do show it to you because it shows that there is a mathematical relationship between the distance between these lines. I want to take a few minutes to talk about what N2 and N1 represent and how that relates to the atom. If you would like to see examples of this equation being used, there is one listed for you in the resources section. Because the energy of the electron is quantized, it can only have certain amounts of energy. This causes the electron to travel in certain orbits. The symbol that we use to represent the energy level is N. So here is N equals 1. That's the lowest energy level. Here's N equals 2. You can find an electron here or here, but you should not find one here in between. An electron can receive energy and jump to a higher energy level, but it must receive the exact amount of energy required to go from here to here. So it's going to jump this high. Can't jump this high. It's going to jump this high. When it's up here, it's in an excited state, and an electron is not going to naturally stay in an excited state. As soon as it gets an opportunity, it's going to fall back to its ground state. So it has to absorb energy to jump, and then it releases energy to fall back down. This energy that's released is in the form of light. And the equation that you saw on the previous slide helps to explain the wavelength of light that is given off when this happens. So just to recap, when an electron receives energy, it jumps to a higher energy level. As soon as it can, it falls back down to its ground state, and when it falls from high to low, it gives off specific wavelengths of light. Niels Bohr is the scientist who really recognized what was going on here, and so this is referred to as the Bohr model. This understanding of the atom is called the Bohr model. The Bohr model is useful for explaining some of the relationships we see between electrons and light, but this model does have some issues. First of all, it only works for hydrogen. When you get to elements that are larger than hydrogen, the assumptions that were made in the Bohr model no longer work. Also, the model does ignore some things about classical physics. For example, if you had a charged particle, like an electron, moving around the nucleus In normal physics, that particle would fall into the nucleus. And Bohr just ignored that. He didn't explain it, he just assumed that it would not happen. The final thing that's an issue for the Bohr model is that circular motion in traditional physics does not have the wave patterns in it that we see in the electron. Even though we do have these limitations to the Bohr model, scientists still refer back to it very often. Here are some things that are still useful about the Bohr model. It showed that electrons only have discrete energy levels, so it really drove home the quantized nature of the electron. It also showed that energy has to be absorbed to jump up an energy level and emitted to jump back down an energy level. So while we recognize the limitations of the Bohr model, we don't totally write it off. There's still some important things about the atom that it helps us to visualize. In previous videos, we noted the fact that light acts both like a wave and like a particle. So scientists began to wonder if matter, which tends to act like a particle, has some wave-like properties. A scientist named Louis de Broglie began applying this to the electron. He noted that the electron, which is a particle, moves like a wave around the nucleus, and so it must have a wavelength. So he came up with a formula that relates the wavelength of the electron to its mass and velocity. And the h that you see here is Planck's constant. In traditional physics, if an object is moving across the room, you can measure its position, you can figure out its speed, you know its location, you know its direction. Scientists wanted to be able to do this same concept with the electron. But the electron is so small, it has such a tiny mass and such a high speed that they were running into problems with these models. A scientist named Werner Heisenberg came along, and he came up with the uncertainty principle. And he basically said that on the level of an electron, since it's so tiny and it's moving so quickly, it's impossible to know its exact location and its exact speed at the same time. Anytime you take a measurement, there's some degree of uncertainty in that measurement. There's some wiggle room in the measurement. Well, on the level of the electron, when they were trying to measure the location of the electron, the uncertainty, or that wiggle room, was larger than the radius of the atom. So it was really not a very meaningful measurement. Scientists realized that it was impossible to know the location and the velocity of the electron at the same time. Heisenberg's uncertainty principle resulted in a shift in the direction of the experiments during that time. Instead of trying to find the exact location and speed of the electron, scientists began focusing on the wave nature of the electron. They also gave up on trying to pinpoint the exact location of the electron and instead began describing it in terms of probability. They started looking at regions of space where the electron was most likely to be located, which led to a new model of the atom that we're going to discuss in the next video.